As electronics engineers, we face the need of multiple voltages through our design, whether variable or fixed. Even though fixed regulators often give us the required values, especially when working with digital logic, there's also situations where we need different values than the ones offered by the manufacturers. Here's when the variable output regulators come in handy. In this case, we are going to analyze one of the most popular regulators in the market, the LM317. This is a variable output regulator with an output that goes from 1.25 volts to 37 volts and a max output current of 1.5 amps. We must remember that, being a linear regulator, the efficiency is very bad. Along with the low current capability, we must not use this regulator for power applications or any other linear regulator for that matter. Let's see its internal structure. We have the typical internal structure of any simple linear regulator. We have a senior reference of 1.25 volts and which defines the minimum output of the regulator. We have an op-amp, a VGT output, and a temperature protection and current output protection. We can see that we don't have any feedback resistors as they are in fixed output regulators. This is because our feedback network will be defined by ourselves later. With the circuit we have on screen, we can see the typical application of the regulator. We have a very simple topology consisting only of the regulator, two resistors for the feedback network, two filter capacitors, and two diodes for discharge protection, which are optional. The output voltage formula is the following, being Vref the internal reference of 1.25 volts, R1 being a recommended value of 240 ohms, and a I adjustment being 50 microamps. Being Vref and R1 a constant in our circuit, we can calculate the R2 value with the following formula on the screen. For example, if we want a 5.3 volt output having R1 with a value of 240 ohms, our formula goes as given in the screen and we get a result of 777.6 ohms. We can see that implementing the regulator is quite easy, but even with that fact, we must always check the datasheet to see other important values to define whether or not the regulator is optimal for the required application. Let's check out the datasheet. In the operating values, we have the output voltage range, being from 1.25 volts to 37 volts, an output current of 10 milliamps to 1.5 amps, and a temperature of 0 degrees Celsius to 125 degrees Celsius. Then we have the thermal resistance, being a value of 23.5 degrees Celsius per watt to 37.9 degrees Celsius per watt for the TO220 case. Then we have the electrical characteristics. For the case of line regulation, which means the variability of the input at any given load, the value is set from 0.01% to 0.07%. Then we have the load regulation, which means the variability of the output at a given load, being from 20 millivolts to 70 millivolts. Then we have the thermal regulation, where we have values of 0.03% to 0.07% in function to the dissipated power. For the values of adjustment current, we have a typical value of 50 to 100 microamps, in changes of 0.2 to 5 microamps. We must remember that this value has a low impact on the output value. For the voltage reference, we have a value of 1.2 volts with a variability of 50 millivolts. This is the internal voltage reference. Then we have the minimum load. This means the minimum load or current consumption required for the regulator to work properly, in this case being 3.5 milliamps to 10 milliamps. We can see that this regulator is not appropriate for low power consumption. And at last, we have the maximum output current being 1.5 amps. Now, a very important fact about this. This value is only guaranteed if the regulator is below the maximum operating temperature, being 120 degrees Celsius. The issue is that the regulator being so inefficient, this operating temperature will go up quite quickly. For example, if we have an input of 14 volts and an output of 12 volts, the input-output difference is 2 volts. If we have a load of 500 milliamps, we have a dissipated power of 1 watt. If we have a thermal resistance of 30 degrees Celsius per watt, we have a temperature increase of 30 degrees above the room temperature. But if we have an input of 14 volts and an output of 3 volts, we have a difference of 9 volts. With a current consumption of 500 milliamps, we have a dissipated power of 4.5 watts. With the thermal resistance of 30 degrees Celsius per watt, we got an increment of 135 degrees Celsius. We can see that the temperature will be a major factor with this regulator, and why a heatsink will be required in many cases. This is the biggest issue with linear regulators. We are very limited by its low efficiency. Well, now that we have seen the most important parameters in the datasheet, it's time to go to the lab and test those values. Let's check the behavior on the following cases: normal operation, max current versus voltage difference, and output accuracy. Do you have a project that needs to be finished? Do you have an idea for a product and you want to take it to the next level? We are your best choice. In Prisma Network, we have the best team to do so. We offer services on hardware design and software design. From PCB development, firmware development, app development, and desktop development. We offer competitive prices and an excellent service. Contact us to get a quote. All of the info available at the video description. So here we have the voltage regulator operating under normal conditions. We can see that we can modify the output voltage. We have both multimeters reading the output. And this is the most common application of the regulator, just modifying the output for low current loads. So now we have the case of the max input and output and the current consumption. So here we have the operating temperature of 71.5 degrees Celsius with a around 2.2 volt input and output difference and a 0.3 amps of power consumption. So we can see that we have already a considerable high temperature of operation, obviously without a heatsink, but we can see how quickly the temperature rises up. And now with a higher difference of input and output, we can see that with a lower current, we are operating at a higher temperature, almost 100 degrees Celsius, or already at 100 degrees Celsius. So we can understand here how inefficient the regulator is and why it is not fit for power applications. Now we have the accuracy and stability test. The regulator has been running for an hour and we can see that the output stability is kind of stable, let's call it that way. I set up a 12 volts output and we have a 20 millivolt deviation, let's put it that way. So the accuracy is respectable, although this is not a regulator that we will be applying for accuracy applications. So it's a good output, but we cannot expect much for something so cheap and so primitive like this regulator. Well, it's time to end this video, and we have to make a conclusion. These regulators have the advantage of being very easy to implement in any design, with minimal components, generating very small noise, and requiring a very small footprint. But these advantages go away at the time we require more power, so let's just keep them away from power-hungry applications. Even then, they are worth the low price and simple implementation parameters.